Well, see, before, when we separated, we were writing, say, f sub x or f sub y for partial derivatives. So now, I see. So you probably mean to say is that when we would write it, we would use this other d. We would use this kind of curly d. And now we are using this d. Well, because the reason is that this is really just d of x. This is really like a differential. So here there's no ambiguity. The ambiguity arises when you have a function which depends on two variables. So then you have to say df with respect to x or with respect to y, right? But here we're taking dx. F doesn't depend on anything. So there's no, we don't have to give any additional information about that. So it's just a differential. When you have a function one variable, we still write just a straight d, right? So x is like a function of itself. So that's why dx. It's the same dx which we use in the differentials actually. So it is with dx and not this dx. But for now, just think of it as notation. Don't read too much into it. Okay? Any other questions? Yes.
So the notation be correct if we wrote a straight df or a straight dx.
Here.
Like what we wrote there. Does it be the same thing?
Okay. Well, I have to say that now we are studying integrals and not differentials. You should have asked me this question when we study differentials. But since you asked me, I will answer it. But think of this. Think of this as a digression, or think of it as a time machine. We're going back in a couple of weeks when we talk about differentials. So remember, df is f sub x dx plus f sub y dy. So in principle, you could write df dx, and this would be f sub x plus f sub y dy dx. Right. So you could do that. So and that, by the way, is related to the derivatives of implicit functions. So, but this is not the same as df dx, which is just the notation for f sub x. See, here there is an additional term. Because the differential has two terms, one related to fx and one related to fy. So you could divide this, it's okay. You get this expression for what it's worth. And in fact, this is a good way to find dy dx. When you have x and y constraint, for example, if you know that f is equal to 0 or something, f equals some scalar. That gives you a way to calculate. That's how you get the formula dy dx is going to be negative of fx divided by fy. This is the formula we studied when we talked about implicit differentiation. Right? But this, on the other hand, with curly d, is just a new notation for f sub x. So that's the difference. But in some sense, this is related because actually this is the same dx as this dx. But it's not like df, because this is not like df. F is actually outside of the differential, right? This is just dx. And for dx, we don't use, like this doesn't exist. Only this exists. This does exist. Okay? Yes? Can I explain it? Okay. I would love to, but I actually have something planned to talk about, so maybe in the office hours? All right. So, but maybe, it might be that this, what I'm going to explain next is example from the book. So, but let me take a look maybe. Number 2, Well, example number 2, by the way, is like just like this one, right? It's just a slightly different function, but it's actually very similar. But let me move on actually to a harder example, a more difficult example. So what else can we do? So for now, the region of integration in this example and in example number 2 is a rectangle. Okay? But we are actually going to study more complicated regions. Because, well, we know that on plane there are many other regions as well. So what can I do here? So the next thing we're going to discuss is how to apply this to compute more general integrals for more general regions. So, for example, suppose that you have the following region. It's defined by the following formulas. Okay? So let's draw this. So x is from 0 to 1, and y, for each value of x, y is confined within this value and this value. So to sketch this region, what we need to do is we need to sketch the graphs of these two functions, y equals square root of x, and y equals 2 minus x. So the first one is going to look like this, because I only look at it on this region, on this interval. And 2 minus x will look like this. This is 2, this is 1. When we say that y, for each value of x, y is confined between square root of x and 2 minus x, geometrically this simply means that it lives on this little vertical interval. And so our region is just built from this little vertical intervals. It is just this domain, this region, this shaded region. So that's more complicated than the regions we have looked at so far, which were simply rectangles, like a rectangle like this. So how do we approach this? How do we calculate the integral when the regions are given by such formulas? So the point is that to compute that, we just slightly generalize our formula. We still do it as an iterated integral. But we first integrate over y, but we integrate with the bounds of integration explicitly depending on x. Namely, we'll go from square root of x to 2 minus x. And then we'll put our function f of xy dy. You see, now before, the bounds of integration were, say, c and d. They were fixed. But now the bounds actually depend on x, because that's the way the region works. We integrate over, for each value of x, we have a certain segment or interval in y, and we're integrating over this interval. But the interval itself, the bounds of this interval, actually depend on x in this way. So there's no problem because we're integrating over y. So it is okay if the limits of integration depend on x. You certainly wouldn't want to put something depending on y in here, but putting the limits, which are functions of x only, is okay. So the result of this calculation is something which depends on x, and it depends on x for two reasons. First of all, the function f depended on x. So even in the old calculation, when the limits were constant, the result was a function of x. But now there is a second reason why it depends on x, because the limits also depend on x. After you compute this, you get a function of x, and then you integrate this function over the limits over the region given for x, and that region already is independent of y or anything else. It's just constant, 0, 1. So that's the formula. It slightly generalizes the old formula, in that we now allow the limits to depend explicitly on one of the variables. So let me calculate this integral in a special case. Let's say f(xy) is 2xy. So let's do the let's do the inner integral from square root of x to 2 minus x. So you have 2xy dy. So that's take the antiderivative of the same rule as before. Take the antiderivative of this function. Antiderivative of this function is x times y squared. Right? Because x is a scalar. And now you have to take it between 2 minus x and square root of x. So what do we get? We get x times 2 minus x squared minus x times square root of x squared. What do we get? We get 4x minus 4x squared plus x cubed minus x squared. So we got this. So we got x cubed minus minus 4. Yeah, minus 5 x squared plus 4x, right? So you see the result is just a function of x. I mean, this calculation is not much more complicated than the previous calculation. The only difference is in the previous calculation, the limits were 0 and 1. Okay, so you substitute 0 and 1, and you get a function of x. Now the limits are square root of x, 2 minus x. But again, you just substitute and you get a function of x. You are going to get a function of x anyway. You might as well allow the limits to depend on x also, right? So, yes? Very good question. Just, I'll explain in a second. I'll just finish. Let me just finish this example now. So what's the end result? We just substitute this into the outer integral. So we get 0, 1, x cubed minus 5 x squared plus x cubed. Right? So this is going, oh sorry, dx. So that's 1/4 x to the 4, 4th minus 5, 3rd, 5/3 x cubed plus 1/4 x to the 4th from 1 to 0, which is 1/4 minus 5, 5/3 plus 1/4 x to the 4th. Sorry, 1/5. Okay. Oh yes. All right. So all of you and just me. Yeah? So okay, okay. You were right. So 4x, right? So that's going to be 2x squared. So plus 2. Is that okay? Okay. And then I'll let you calculate this. Okay. Now, this actually begs the question which you asked, which is it possible that we would have at some point encounter integrals in which, for both inner and outer integral, there will be some dependence of the limits on x and y? So let me answer this. The point is that this will never be necessary for the following reason. So the most general, let's look at the most general domain. The most general domain could look something like this. So the point is that I can always break it into what the book calls regions of type 1 by cutting it by vertical lines in a sort of smart, in a clever way. I break it here into 5 pieces, and each of the 5 pieces can be represented as a region of this type. You see. So all of them can be thought of in this way. Well, in this case, that would be like it touches here, but it doesn't. This would be the, for example, for this one, it would be, so this would be some function y equals f2 of x, and this would be y equals f1 of x. So here you would have y equals f2, and here you would have y equals f1 of x. So when you have this region, what is the description of this region? The description is that x goes from a to b. See, no dependence on anything, right? But for each x, the values of y are bounded between f1 of x and f2 of x. For example, in this case, f1 of x was square root of x, and f2 of x was 2 minus x. And any region can be broken into such, and so therefore, then the integral will be equal to the sum of integrals. It goes without saying, of course, that if you take an integral over this entire region, double integral over this entire region, this will be the sum of the integrals over the pieces. When you decompose it into a disjoint union like this, of non-overlapping subregions, then the integral can always be found as the sum of the integrals of the parts. Integral of the whole thing is the sum of integrals of its parts. And then each of those guys you can represent in this way. Then, of course, the point is that sometimes it is advantageous to represent it not by cutting by vertical line, but by cutting by horizontal lines. And this actually gives you a way to, gives you sort of a second way to evaluate your integral. And sometimes it can happen that one way the integral is very difficult to compute, but the other way is much easier. So let me give you an example of this. Here's an example. So suppose you have the region like this. So you have xy, where y is between 0 and 1, and x is between, x is between 0 and 1, and y is between 0 and x squared. And you ask to compute the integral of the function square root of x cubed plus 1 dA. Okay? So let's draw this region. So x between 0 and 1, and y between 0 and x squared is a parabola. Like this, so this is the region. This is 1, this is 1, and this is, right? Okay, so since it's written in this way, we can write it down as an iterated integral in the same way as we did in the previous example. So that means we would first be integrating x over x, right? So that would be, not the first, outer integral would be with respect to x. But the inner integral would be with respect to y. So that would be from 0 to x squared, square root of x cubed plus 1 dy. Right? So let's compute the inner integral. So the inner integral is okay, so this function looks very complicated, but remember, we're now integrating over y, so this is a constant. So constant function now, because x is frozen. So the antiderivative is actually this constant, so to speak, because it's independent of y, times y. And then you do it from 0 to x squared, so you get square root of x cubed plus 1 times x squared. Right, and now you have to integrate the result, which is very easy, because you can introduce a new variable z, which is x cubed, right, and then dz is 3x squared dx, so that this becomes 1/3 of dz. And this becomes 1/3 of z plus 1 dz, right? Which is very easy. Okay, I'm just trying to save time because I only have 2 minutes left. So this is easy, but don't do that on your midterm. I have an excuse because I don't have enough time and I want to explain something to you. So here's a tricky question which you'll find on the homework. The tricky question is the following. Let's think of the same region. Let's think of the same region, but from a different point of view. Let's cut it by horizontal lines. If we cut by horizontal line, the same region would be x, y, where now y is between 0 and 1, and x is between what? It is between the square root of, so this y, that's right, between square root of y, right? Right, and 1. You see? So if I do that, then the same integral will be written like this. So now this would be the outer integral will be with respect to y. It's always the case. The variable which is between, for which the limits are independent of any variables, which are constant, like 0 and 1. This is the variable which is the outer variable, outer integration, variable of outer integration. And the inner integration will be from square root of y to 1, right? And then the function will be x cubed plus 1, same function. But now we have to integrate this with respect to x. And we see this is much harder. Right? This is hard. Because it's not clear what the antiderivative is of this. See how much, now you can appreciate how much easier it is to calculate the antiderivative of this function with respect to y. Because y doesn't know about x, right? So this is a constant, so you're doing the antiderivative of a constant function. That's why you get this very simple function, and then you luck out that you get x squared, so it becomes much easier. But here, you get a function of x, and it's not clear what the antiderivative is. You see? So you have to be aware of this, that there are 2 different ways to compute, and one way could be much easier than the other.